I think we should get started. Hello everyone, I'm Ayush Kumar Tyagi. I'm PhD student at IIT Delhi and I'm TA for Modern Computer Vision, and today we will be looking at the last topic, which is visual language models, and this is the first part of the lecture. In the second part we will be looking into the few of the problems. We'll see few sample problem which will basically span like whole syllabus. Yeah, so let us get started with the visual language models. So till now what we have seen is there are like image detection, object detection kind of architectures which basically uh, revolve around or depends upon images, where image is the input to all these architectures. We have seen the other class of architectures which are basically language driven, right? Like some sort of sentiment classification models where uh, the text is basically in the image. Sorry, the text is in the language is the text, and the output can be one of the classes, right? Um, we have seen the recent trend where the chatbots like ChatGPT has shown a significant growth, like when it comes to like understanding the context and giving uh, the appropriate responses. So these models are basically called as the language models, right? Examples are ChatGPT शायद ChatGPT another these like other models as well. So every major company has different language models. So this is ChatGPT is OpenAI. Then you have Gemini is there. You have uh, is from Google. Then I think Lava is from Meta, I guess. And yeah, these are the major, and in the even the Anthropy AI has Mistral. Um, there are many companies who are working on this language model, and the recent the advancements are basically coming in this like from this direction. Uh, but many you see that language modality itself is not a complete without the visual perception. So people are actually moving towards the visual language model where you along with the language you have information about the visual scene of the surrounding, and there are many applications for that. Like you can actually ask what are you observing, how many objects are present in the surrounding, and the conversation actually becomes in a more natural way, more aligned to the human way of communication, right? Suppose like even in the chat gpt also you can actually input image and you can ask questions about it. Maybe you want to create a website. What you have done is like you have taken a snapshot of the website and you say that can you uh, create web page similar to image, right? So like you're referring to this image whenever you're asking any question, right? So this uh, image and language interaction is basically taken care of this vision language models, right? And there are applications like text to image generation, like diffusion models. So where you have text, great image of lion football, and it will generate you an image of the character and the football, right? uh, this is text to image generation. uh, right, so this is our first application. Second is basically the visual question answering. So this is basically uh, the chat gpt is one of the example of that. Even in the medical images, medical field, there are methods where, so they're called the path chat, where you can actually upload an image and you can uh, talk about what is the diagnosis about the image. Maybe this is a x-ray image. The image, you can ask, can you comment on the tumor, right? uh, then it will give you a response. Then based on that response you can basically ask another question, can you localize it? Right. So this is visual question answering, and like the question answering, it's more of a conversation based problems, right? Where you have images, and you will be always going back to image to give some sort of assessment, uh, right? And third is basically image captioning, image caption generation. So in image caption, the input is image, but output is a text. So maybe you want to post a picture on your Instagram account, and what you do is like uh, you upload an image and you say that like suggest some captions, and your model should be able to give you n such captions with some sort of a scoring mechanism, and you should be able to pick whichever suits you best, right? So all these are examples of vision language model, and what you can do is there is many applications, and it is basically a more intuitive way of understanding what is happening in the image or text, and the conversation between the AI and the human is more natural when we are doing it in a vision language. Like the model has the information about language, like what we are trying to ask. Model have information about image from where we are going to ask, and then it is able to give you the responses. So there is a, even in the robotics also there is a field like vision text guided robots, where like you want your robot to perform a task, and suppose you're saying that like just go, so there's a uh, cup which is being placed there, and you want your robot is standing here, and what you, the task is, the text input is like pick the cup. Okay, this is the cup, this is the text information which is being fed to the robot. So robot also have a visual information of the surrounding, and robot generates a plan that what are the steps I need to do so that I am able to reach the cup and pick it, right? So even when you are actually going closer to the cup, the robot can actually see that what, by what degree I have to move my hand so that my hand doesn't spill the coffee. Like I have to be very careful when I am picking it. If there's this, if I have hold the cup in the wrong way and the coffee is spilled, I need to correct myself right? So all this information, all the feedback basically coming from the visual information. So both language and vision are very essential to whatever uh, the way things are moving. So it's very good field, and like very interesting as well. So what we will do is like we will be looking into few of the vision or language based architectures. Let's start with BERT. So BERT is basically a text. It is basically the language model, and it is language model. This is in the encoder format, and it is based on transformer architecture, right? So right, so there are two phases of training a BERT model. So first one is the pre-training, where what you do is like you train with large data set in an unsupervised way, or unsupervised supervised, or some sort of a semi supervision actually. Right. uh, you So what, suppose one of the task is basically you have two sentences, and what you say that like whether this is sentence A, sentence B, and you say that like whether sentence A and sentence B are basically related, or maybe the sentence B is the continuation of sentence A. This information is present in the uh, in the internet, in a there's a vast amount of information, right? So like maybe what you next word prediction, next word prediction, right? Next word prediction is something, right? So we have given you 10 words. Based on that, like can you actually guess what is the 11th word, right? There is something called as this is fill in the blank kind of a problem. Next is like suppose you have sentence 1, you have sentence 2, then you say that like whether sentence 2 follows sentence 1, right? Or maybe sentence 1 and 2 are related. So this is basically the problem of next sentence prediction, right? And um, correlation. Okay, so what is the structure between the sentences is something what these language are pre-trained on. So what is happening is like you have large amount of unstructured data. You'll just pick anything these sentences from the web, clean them, and create certain tasks. Suppose in this case, what they have done is like the next sentence prediction task, where they say that like if the next sentence is related to sentence 1, right, sentence B is related to sentence A, and then just pass on both the sentences, and your model should output whether both of them are related or not, right? So what it is predicting three things. One is basically the next sentence prediction, whether it can be 0 or 1, a true or false kind of a situation, right? uh, Additionally, what they do is like within the sentence also they mask few words in, right? So suppose there were 5 words in the sentence A, and maybe 6 words in the sentence B, and what you do is like you mask few of the sentences, like suppose Hello. Okay. So I was just talking about like language models, and we are basically looking into vision language models. Um, and In this slide, it is BERT, right? And BERT is basically a language model. And what is happening here is we are trying to predict. Let me just go one step back and give you what's happening here. So we are talking about BERT. It's a transformer-based architecture, and what we are actually looking into is pre-training steps. So what BERT has been pre-trained on, it has large amount of web data, right? And people have actually extracted that web data, cleaned it up, and what they do is like they simply pass this in the text into certain questions, like suppose there are two sentences, one is the sentence A, the other one is sentence B. Can you actually tell the sentence B follows sentence A, right? So this is basically the next sentence prediction task, right? Similarly, like within a sentence you can actually mask out for certain, within the sentence you can actually mask out certain words, right? And the language model will be predicting out those masked words. So basically what is happening here, we are training BERT on two objectives. First one is next sentence prediction, and other one is the mask prediction, right? And right, and there is something called the self attention mechanism, which is essential to, this is the self-attention mechanism which is essential to these problems. Like what is like, how does uh, what is the importance of all the word with respect to even then, like you do it for all the words, right? uh, and you use this information to predict what is your next word, or like maybe when you are actually doing some sort of a translation task, you have in the input you have sentences from English, you want to convert it to French, and like this is some sort of. But for this, you need to have a paired information. So this is the first step, right? The step one is the pre-training, and you have done it for the large data set. Now you have a pre-trained model. What you do is like you fine tune it onto some particular task. So right, so basically uh, what is happening here is like you have the question, you have, suppose you have paragraph, and you have the question associated with the paragraph, and you what you do is like you want to answer certain question, or like so it is very similar to comprehension problem where you have images, sorry, like you have the big paragraph, and there are certain questions related to the paragraph, and your job is basically to answer those like questions. And this is what right, this is what they are doing in the fine tuning. So NER is basically name entity recognition. So you have the image, you have the text, and what you want is like you want to identify what is the name, what is the entity, right, and what are the attributes of the entity. So those kind of problems basically you are able to solve. Even in this, you have a translation problem also comes into it, like the language translation, right? And like there are many applications, right? But the whole uh, thing that actually worked for BERT before LSTM or those kind of architecture is this pre-training step, right? And people have actually pre-trained it on the large, vast data set, and that's why like it is able to already learn certain nuances about the language. So, like you have seen that like the grammar is very good. So, in the, even earlier models of the Chat GPT, the grammar was something which these models were very good at, right? So, like the grammatical structures they have learned in the unsupervised manner. Like now people are actually pushing these language models toward the reasoning task, but that will come eventually. But like the overall structure, and it has already mimicked or learned the whole data, like they scrapped whatever the data which was possible on the internet, and pre-trained everything, right? So if you scale BERT, it uh, it will have the similar performance as compared to the GPT, right? So, but here the BERT is the encoder model and GPT is a decoder model. Next is vision transformer. So what we have seen till now is basically the language encoder. So people generally use vision transcoder transformer as uh, vision image encoder basically. And it also works on basic on the principle of transformer only, right? uh, and how do you, I think this paper is each word is each image is 16 cross 16 word, something like that, right? So this is the name of the paper, and generally in the short form it's popularly known as the vision transformer. So what people generally do is they split the image into multiple grids, right? And for each grid you learn a linear projection, right? So something like this. So for this grid you'll have this information, for this grid you'll be learning this embedding, right? So for all of the patches you learn different embeddings. Additionally, what will happen is, like, since we have like created patches, we have removed the spatial structure, spatial information. So what they have done is, like, they have added the positional embedding as well. So positional embedding, what it does, it basically gives you the information about where was the location of this patch. So suppose this is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, and you have added this information along with your patches. So the zeroth is basically learnable embedding. Embedding, it does not correspond to anything, it's just called as the CLS embedding. Right. So you will feed in all the information, you have multiple layers of encoder, this, so, right? And you have multi head encoders present inside it, and what you do is, like, you'll have it will provide you some sort of embedding, you'll provide it to the MLP head, and it will do the classification, right? So this is our vision encoder. So and the whole thing is, like, you have things which actually work for these kind of architectures. For transformer based architecture is that, like, train them on a large data set, and they like learn a very good representation, and you can actually use into multiple downstream tasks. You can actually fine tune them new tasks, right? And it does pretty well. So the question is, how do we actually like use both the information, and what can we do about when we are basically using it? So one of the model which was early model which was released by OpenAI was Clip, right? And what they generally do is like they do this contrastive language image pre-training, uh, and what you do is like you have the text encoder. Suppose it's some sort of a transformer based architecture, right? And it has it basically provides you uh, some sort of a embedding of the text which is given to it. You have the image encoder as well, right? And it will also provide you the image embedding. So what they are trying to say is like we will use the contrastive loss to minimize the distance between the text and the image embeddings. So right, so this is what they are minimized. So this similarity has to be highest, highly similar. It's highly similar. Makes sense, right? Right. And and you want to separate, you want to ensure that like uh, the other pairs have the lower similarity. So you do some sort of a similarity matching, and they it is done by something called as a contrastive contrastive loss. So you have the embedding, uh, maybe E, let's say it's I1 T1, right? And exponential of, with respect to exponential of I1 T1 plus I2 I1 T2 with respect to all the negatives. So these will be negative pair, right? And I1 T1 is a positive pair. So what you want is to learn is that this positive pair has the high similarity, and the all the negative pairs I1 T2 I1 T3, right? You should have a lower similarity with respect to this, and you want to minimize this loss function, right? uh, okay, so this is what contrastive loss does, and Clip basically is using this information this property, and training it in the image and text pair. So you have images and you have the corresponding text or captions associated with the image, and you train this clip model so that like you have the similarity. So once you have done, you have learned this kind of embedding. So you will see that like even in learning it in an unsupervised way, you will see different clusters which are being formed, and each cluster represents some sort of a structured information about like maybe one cluster is basically breed of dogs, so other cluster is basically cat, and you will see that the gap basically between these cluster define how well separated these clusters are. That means that like model has actually identified on what basis it has to uh, check the similarity, right? And what are the pairs which are basically very similar. So once now you have done, you have learned uh, the like the pairs, you have learned the embedding, you can actually use it even as the image encoder or the text encoder. So and use it for a downstream task. So maybe um, what you say, uh, you want to ask questions in yes or no. What you do is like you pass on the image and you pass on the question that is is this dog black and white. You pass this information into clip model, it will give you the embedding, and this you pass to the classifier which actually says yes or no. So you can actually fine tune it on the multiple type of tasks, right? So what they have done is like they are using basically the zero shot prediction. So what you do is like you have the image, uh, you have an image and you have uh, right, you have what you have, yeah, so you have labeled text, you have the information, you'll just what you do is you will pass this information, this is a photo of, and you simply keep it blank. And what the text encoder do is like you convert text into the embedding format, and you do a similarity matching between the image encoding I1 and all the embeddings which is present, which is provided by the text encoder, and you pick the one which corresponds to the highest similarity, and um, and you'll just simply you know, right, like what this embedding basically corresponds to, and trace back to what is the objective. So this is a dog. You can actually use it as a generative in the generative task as well, where given the image it should basically identify the closest embedding clue to it, and that embedding it should be able to convert it into the words, or even in the text to image task where you have given a text, you'll get the representation of the text, and what you want is like you want what is the closest image embedding will be, and can you actually go and generate it. So those were the like interesting applications for it, right? So one of the tasks which was very one of the data set which is common is this clever data set where you have certain objects, and it's basically more of a reasoning side, right? So you have the image and you have the questions associated with it, and your objective is to ask them, give them the answer, right? So suppose there are an equal number of large things and metal spheres. So you have to identify how many metal spheres were there. This is one metal sphere, this is two another metal sphere, and how many large things were there. There is one large thing, two large things, three large things, right? So the answer is basically these kind of reasoning you are actually required to do to solve this task. And you'll see that like even the images, these variations are like in term of this is different material, this is metal, this is rubber, right? And this is different type of object, this is cuboid, right? And this is circle or sphere, this is cylinder. So different type of objects are there, different type of made from different type of materials, and basically you identify them, what are the type of material, what it is type of. So like even for this task, like you require equal number of large things, so you need to have a understanding what does the large thing means. So you need to understand the concept of metal sphere, right? And you need to understand that like what is the equal, mean. So these three things you should have understanding, and this understanding basically these equal basically the understanding of equal might come from the language, the correspondence for this large thing metal should come from both language and uh, images, and you need to learn a correspondence from language to image, right? So one of the possible architecture for this is you have image encoder, right? And then you have image embedding, you have text embedding. What you do is like you do some sort of a cross attention between them, and you have you take this embedding, pass it on to a decoder, which is essentially a classifier, and it predict the class, highest probability class. And this is one of the possible architectures. So you are at this step you will be learning so the what is the correspondence of text with respect to image. So using this cross attention module, the cross attention also you can have multi-head, right? So this is what a language model interactions look like. There are other examples. The recent trends are following this uh, like way of modeling things. So yeah, it's very useful. In next we will actually go and see what is look into the problem solving, solve few of the questions here. Right. So the first question is middle layer of the CNN's neural network learn to detect features such as edges. So we remember, right? Like CNN has filters which detect certain patterns, right? And what are the possible filters? This is like Sobel filter was something which people were actually. So what happen generally in the CNN layers? Your initial channels, initial layers basically learn to identify edge, right? And the middle layer basically start to uh, get a sense of small regions based on the edges which are detected in the first few layers. And then the last layers, actually start making sense of what is the objective, right? So suppose you want to do some sort of a classification problem of maybe a dog, right? So if you want to do some sort of a dog classification, task, what you do is like the initial layer actually get some features like edges, some texture, right? So the middle layer actually start to learn what does the eye of a dog look like, what is the nose, ears, paws, right? So the attributes of the dog, and all those things will basically combine, and the final layer actually start to make the decision. Yes, there's a region which looks like a dog is present there and it classified as a dog. So so this statement is false basically. So the next question is that is a derivative filter always sums to zero. So what are the example of the derivative filter? So 1 0 1 example of Sobel, I guess. Right. So if you can basically see the sum is equal to zero. Even the other filters like -1 2 -1 1 a derivative filter is always the statement is true. So given two ring of points where rings have equal center, so both of the data points have concentric centers and average point value, right? So the k means with Euclidean distance and k is equal to 2 will never be able to separate the rings, uh, separate the ring, so each cluster containing one ring. So what they are saying is that like, well, the k means will be ever able to separate it in this way, where they say that like this is class 1 and the internal of this class 0. So let us see how does the k-mean work. So what happened in the k-mean? You initialize the cluster, initialize the cluster center to the zero, to the center point, and you identify which the points which are closest to its the center, and you assign your you update your cluster. Since both of them have the concentric circle starting points, so what will happen is like you will assign which is you identify the distance with respect to this point, you identify distance with respect to this point, right? uh, Both of them are same, like, right? So there will not never be a mean update, and hence this decision boundary which we were actually thinking is basically is not going to happen. So what is going to happen? Everything has been will be put into a single class. Right. right? So this is one of the failure cases of k-means algorithm. So this is false. What does it say? It will never be able to write. So it is basically true. So this is question number 4. So consider the case of running Harris corner detector on a patch of chessboard images. The white square has two values and black square has value 0. And if you can assume that the square window function w x comma y is equal to 1 everywhere in the patch, then and the, and that the patch used to compute the second moment exactly is 2 cross 2, right? So right, so if you go in the next page you have this. So the red patch what we are seeing is basically p is 0 comma 2 2 comma 0, right? So suppose what if we are looking at only the region where it's all black or all white, so the intensity will be something like this. So this is 2 2 2 2, right? On the edges what will happen, right? On the edge you'll have on the one side it is 0 0, on the other side you'll have 2. So this kind of intensity information you have. So right, uh, so the patch matrix look like, the red patch matrix actually look like it is it is 0 to 2 0, right? This one. And what you have given is like you have dx and dy which are our derivatives, derivative filters. So what we are required to ask is what is the second moment. For that what you need first moment, right? So, and what is the formula for second moment? So it's basically summation over x comma y w of x comma y I x comma y whole square I x comma y x comma y I x. So this is the second moment matrix, and here I x comma y I x is basically our the first derivative. So so what we have is we have p 0 2 2 0. This is what we have, right? Yep. And we have derivative dx is equal to 1 0 minus 1 dy is equal to 1 0 minus 1 transpose, and we can actually do the padding as well. So let us do the zero padding. Maybe let us see if we can actually do this. And you convolve it with the filter, then ix should be let us see, first place will not have anything 0, then the second place will have -2. If we'll keep on moving, we are placing center at 2, right? You have 0. Again we move to the next row, -1 0 1 2 here, right? This is -1 0 1, this is 0 again. So do 0 1 -1, you have 2 here, right? And 0 0 0 here. So we will take this 2 cross 2 central matrix for our analysis. -2 0 0 2. Similarly, we will compute for IY, and if you compute it, it should turn out to be same. Yes. Right, so you have right ix whole square. What we'll do is, like, we'll just take the determinant of, like, only the diagonal values basically. So 2 square minus 2 whole square plus 2, and this is I y x comma y whole square, that is -2 whole square plus 2 square, right? Then you have I x comma y y I y x. So we'll just need to multiply. This is 4 0 0 4, I guess. Similarly, you'll have the matrix here as well. Right, and what we'll do is, like, you'll take the determinant. We'll take this one over. is m. Okay, and what are the eigenvalues for this m? So how does she compute the eigenvalue? M minus lambda I equal to 0. 8 minus lambda should be equal to 0. 8 minus lambda whole square minus 8 into which should be equal to 0. So you have lambda square minus 16. 16 lambda plus 64 minus 64 equal to 0. Lambda square minus 16 is equal to 0. Lambda is right. So eigenvalues are makes sense, right? So next is like, is this a corner or not? So let us see what is the R matrix. So I think what was it? I think it was determinant of m minus minus k into trace of m whole square, I guess. So determinant of m is 0, where m is 8, 8, 8, 8. So 0 and let us say k. Trace is basically the eigenvalues. So 16 square 0 minus k is 256. If it is basically less than 0, right? And if r is greater than 0, then it is a corner. R is close to 0, it's a flat surface. R less than 0 is, I think, is edge. So we can safely say that the patch is cannot be classified as a corner. So this is false. I hope it is clear. So now next question, you have come up with a CNN classifier for each layer. For each layer, calculate the number of weights, number of biases, and the size of the feature map. Right, where you have the notation, which is on k is, I guess, is the size of a filter, and n is the number of filters. and you have padding is equal to 0, stride is equal to 1. So in, for a n cross n image, w cross h image, you have w minus f plus 2p divided by s plus 1. So padding is equal to 0, stride is equal to 1. For us, with the formula is n minus what is h minus s plus 1 or w minus s plus 1. This is our formula, right? In pooling, the stride is k, padding is equal to 0. In fully connected neurons, you'll have n neurons. Right? Let us start. So you have the input image with 128 cross 128 cross 3, number of weights 0, bias is 0. So then what you do is like you pass this input image with a 9 cross 9 convolution filter, and there are 32 such convolution filters, right? So 128 minus 9 plus 1 divided by 1 is your output, that is 120 cross 120 cross, and there are 32 such filters, right? So 32 is the number of channels. What is the number of weights? You will have n 3 cross 9 into 9. 9 to 9 to 3, right? And number of biases. So each filter will have one bias. So I guess 32 biases should be there. Biases should be wx plus b. You convolve and you'll have one bias for each filter. Yes. You do pooling. So if you do 2 cross 2 pooling, you just simply make it half. Number of weights here. In the pooling, there are no weights. Again, you do filtering. So you convolve with 5 cross 5 filter, and there are 64 such filters, right? So what will happen is 16 minus 5 plus 1 is 56. 56 into 56 into 64. How many weights will have? Because the number of channels was 32, it should have 5 cross 5 cross 32 5 filter. So 5 into 5 into 32. Biases should be 64, right? And you do the pooling 28, 64, no parameter, no parameter. So again you do the convolution 5 comma 5 comma 64 is what we're convolving. 28 minus 5 plus 1 is basically 24. right? So like you have this many, this is weights for one filter, no? Right, and then you, because there were 32 such filters into 32, there were 64 such filter into 64, now you have into 64, right? This is also weight for each filter. Yeah. And then you have pooling operation 12, 64, pooling as 0 weights, and then what you do is like you do the fully connected layer, right? And you map it to 3. So your pulling, the fully connected stand for convolution with n neurons. So there is 3 neurons. So I think what is happening here, like kind of flatten and map it to 3. So you'll have 3 I guess the output dimension should be 3. Number of weights should be 12 into 12 into 64 into 3, right? And all of them will have a biases, each neuron, right? So we'll have 3 the output, right? So what is happening here, you have the input image and you do a convolution operation, you do pooling, right? You simply reduce the size, you do again do the convolution operation, this is your updated resolution, you do the pooling operation, again you do the convolution, again pooling, and then what you do is like you simply map it to a classifier kind of a situation where the output, you are outputting between the 3 classes. So this is how you do it. Moving to the next question, consider a 2D Gaussian with standard deviation equal to 3 pixels. Which of the following is the most efficient kernel that could capture 99% of the distribution in order to, for a Gaussian, right? If you want to capture the 99% of the distribution, you need to actually look into 3 sigma spread, right? And what is the sigma standard deviation for the number of pixels? So this is equal to 3. So you will need to look into 3 in this direction, 3 into 3 in this direction, and then you have the central pixel. So 9, 9, and you have the central pixel, which is basically 1. So I think this is the right answer. Anyway, it's bold. So you should be able to create a filter which is of 1 comma 19. So it will be some sort of this long filter where you will have some values, will have some sort of a Gaussian distribution, and this should capture the 99% of the distribution, right? So what does the each entry of 128 dimensional set feature represent? It represents the gradient in that day, that orientation. So basically there are 16, the whole grid is divided into 16 part, and then you have 8 different orientation, right, for corresponding to 45 degrees. So a binary image pixel array on the left below is convolved with some sort of a filter, right, and gives the results on the right. Specify the operation by numbers within an array. State its relation to finite different operators of specific order, and identify what task this convolution operation achieves in computer vision. Right, suppose you have an image which is completely black and this is only white, right? And what you want to identify what filter does this have, right? And what is the response you're having? You're having some sort of a edge here and some sort of a edge here, right? This is right. This is the kind of response you're getting in the output. So what can we do about? So one thing is sure it is some sort of a you're computing some sort of a derivative as well, right? So this kind of a response you're getting on both the edges. So what are the derivative filters? Minus 1, 0, 1. Let us try with this f1, right? We'll start with convolving it from here. This point the output should be 1, and if we move here output should be minus 1, 0, 1, 1. If we move here then the output becomes 0. The next also it becomes 0, and then for this it becomes 1 again. So minus 1 and minus 1. So this is actually different from what you saying, right? So let us try some other filter. Minus 1, 2, minus 1. So we'll start at this point. You'll have 1 in the output. Now you have so 0 minus 1, so you have minus 1 here. Again if you move here you will have plus 1. If you move at this place you will have 0. At this place also it is 0. This place it is minus 1, 2, 0, then it becomes 1. If we are at this point it becomes minus 1, right? I hope the same trend will follow in, right? So what is happening here? So the filter of our need is basically minus 1 to minus 1, and what phenomena are we actually looking into? Is basically we are traversing through both the edges. So this is edge 1, this is edge 2. You'll see there's an edge detection here, right? And then we see that like there's a change in the gradient of the other side. So on both the edges you'll see that there's a change in the pattern, right? Okay, let us see what we can actually do for the remaining of the session. We have some time left. These questions we have seen. clip based model. If you are trying to write anything or like creating a code clip, which repo is there? Let me just see if I can find out. Here is what. So the Hugging Face is one of the libraries, one of the places where people have started actually putting uh, your the what you say is your models basically. So you have a space where a lot of models are placed. Let me see if I can actually get something running for you. Just please log in, log in. Let us log in. Um, what was my username? Let's see. I'm trying to log in into it. Let me just give me a minute. So I think this is what a simple, uh, a easy VQA looks like, right? So there's a nice blog about it. What does the easy like VQA looks like? You have multiple data sets, right? And you will be asking, is it? It appears to be raining. It does it? Does this person have good vision? So if, because if it is raining, either look at, you will look at the physical the attributes, like there are either droplet, if the person is carrying umbrella, it's basically opening the umbrella. Those kind of things you look into when you are actually looking into to answer these questions. So does this person have 20 by 20 vision? I think it's 6 by 6, but uh, like you need to focus on the spectacles, right? The person is wearing the glasses, so I think it is not true. Similarly, there are other variations as well. What color of her eyes, what are the mustaches are made of, so you need to understand what does the banana look like, you need to understand what does the mustaches look like, uh, right? And you need to understand what like the attribute, it's a girl, right? So those kind of understanding uh, you need to have, so that like you will be able to answer these questions. So this is simple demo. You can actually generate an image, a teal triangle shape. So what we can do is, let me just generate. So let us generate a random question. Is there a green shape in the image? Let us see if, what does it predict. Answer says no. If the shape is red, answer says no. So those kind of things you can basically uh, like answer, and it's a very simple CNN based architecture. But like when you actually go in a much complex setting, you need better representations of the image. So this is a more complex model. This is the blip paper, and they have done like a decent amount of work in this visual question answering problem. So what they do is, like, instead of, they kind of ground like the questions with respect to image and then predict something, right? um, I forgot the name of the paper which I was referring to, but I think it's a good paper. You should be able to, you should be able to get a sense of what is happening. Similarly, the dataset which I was referring to, it was CLEVR dataset, right? And it has certain attributes. This is the paper. You should be able to see what is happening, right? Like there are multiple questions, right? Like what is the perception of behind or front, right? This is the perception. What is the perception of left and right, right? And there so there are multiple type of shapes. You have large gray metal sphere, large brown rubber sphere, red metal cube, small green metal sphere. You have multiple type of objects which are present, and what you need to do is, like, you need to understand what is the object, where the object is, what is the material of the object, what is the structure of the object, what is the color of the object. Then only you will be able to understand, and you will need to understand the composition, right? Like the brown sphere is on the left side of the purple cylinder which is made of rubber. So these kind of correlations are essential when you are actually looking into this VQA type of architectures. But like I think in the natural images, it's a difficult task. Let me see if I remember what was the paper. Path lava, quilt lava. Similarly, in the medical images, also people are actually trying to do the same kind of things where you have an image and you can ask, can you provide a concise description of histopathology image shown, right? And the model respond that like, okay, this is what happening. Then, like you said, that given the presence of mixture of lymphocytes and eosinophils, what is what can be deducted from a single image regarding the possible diagnosis. So the model actually gives you what are the possibilities of possible diagnosis for this image, right? And like people are actually started to move into this direction where you have a conversation with an agent, and the agent basically gives you what kind of description is present in the image, right? And this is one of the largest data set which has been collected uh, till now for medical images, and similarly the people are actually doing it for natural images, even for what you say the satellite images, and people are actually moving very fast when for different type modalities as well, right? For the chest ray, like a doctor has to see it manually, so people are actually trying to automate the whole process in this field. So there are other particles as well. And, so Microsoft released this large language vision model called the Medlava, and it is open source, so you can actually and does pretty well on the radiology images. You see. So it also does the similar kind of thing, right? Like you have the image caption. What they've done is like they've taken images from different papers or like different reports, and like what they've done is like they have created it in a form of a question answering pair. Where is the lesion located? The lesion is located in the posterior aspect of the right upper lobe of the lung. Is it extended to the chest wall, right? And the answer, the assistant basically answer, can you explain the cavities of the lesion? So this is what they have done, and they have trained the model based on that, right? So I think it's a very exciting field. Like many papers are basically coming up. Even the language chat gpt people have tried, even Gemini we have tried, uh, but like when it comes to these kind of modalities which are not very frequent, these models don't do very well. So yeah, just keep a look at Hugging Face. This is a very good community where people actually put lot of their models. You can get all your like models which these companies release. So Meta just released Llama 4, right? And these models are available on this Hugging Face, right? So there are data sets, there are models, and it has become the standard where people are actually putting out the models. Um, just so this is the archive website where people put lot of papers. So if you go to computer science and search for computer vision and pattern recognition, you will get lot of papers. So these are the recent papers which have been put into the archive. So I mean, if you are interested in about the research, it is recommended that you keep a track of these papers and keep on reading the interesting ones, right? Token focus, uh, VQA based paper, new data sets, new reports. Yeah. So, how can object help language understanding? If you open it, it will be like this. Right. Uh, okay. So this is all I have. Um, if you guys have any questions, just let me know in the discussion channel. And best of luck for your exams. Do well. Just go through the whole syllabus. Ensure that you understand the concept. You do not try to remember things, because those things don't help on in these kind of exams. So understanding the concept is essential. Um, and use your time judiciously. Uh, like if you are not sure, just skip the questions. Uh, Mostly questions will be on the first principle basis. They'll not ask you very difficult calculations and everything. So just understanding the basics will be helpful. Yeah, so that's what I would say. And thank you for taking the course. Uh, if you guys have any questions, any suggestions, put it in the discussion channel. I hope you had a good time learning, right? And yeah, because I have learned a lot for taking these sessions. So yeah, thanks to you as well. Yeah, I think I'll just close it. Okay, we'll close it here. Thank you so much.